recorded. So, okay, I guess from a single cloud to aqua planets to now it's time for a reality check. We go into seasonal prediction of Indian monsoon, and we are going to look at role of ocean atmospheric coupling in how good the prediction of the Indian monsoon is and what it does to it. So this is the outline. First I'll say why it's important to talk about seasonal prediction. That is when you're looking at one number for the entire country, more or less, for 4 months. That's the number that we are going to look at and how good, what information it has for us. That comes from the first one, and then I'll talk about how well the models predict and what are the factors that could be responsible for them to doing very well or not doing so well. And finally, we'll look at something, the season of 2012, which was kind of discussed partly yesterday afternoon. So I thought I'll add a little about the 2012 monsoon. So I guess some of you are familiar with it, those who have seen mine or Sulochana's lectures. That is droughts and GDP. And okay. Which one is? Oh. Yep. Okay. Yep. Fine. Okay. So this is percentage of departure of Indian summer monsoon rainfall, and this is the impact on GDP. This is from a paper by Sulochana and Siddharth, who happens to be her son. And what I would like to point out is that whenever there is a drought, it has a bit of an impact, and this impact was much larger in the decades of 60s and 70s, and this is 2002 when it had a less impact. And people started saying that our economy, this is about Indian economy, when I'm talking of GDP, I'm talking of India's GDP. And so they said our economy is drought proof, but I would like to know what would happen to the food grain production, FGP, and whether it is drought proofed. So this is impact of drought on food grain production, or impact of ISMR variation on food grain production, and this is the departure of ISMR. What I would like to show you are this quadrant kind of basically tells you when the rainfall is low, and this is 1972, which was a major drought, and this is 2002, which means, and if you look at the enormity of the drought, 72 was as strong a drought as 2002, and the impact was comparable. This is 87, which was another major drought. This was 82, and this is 2002, which means that the impact on food grain production is as large today, that is in the last decade at least, the last major drought that we had in 2002. This paper was in 2006, and obviously after that there are numbers which we have not added, but certainly it looks like the impact on food grain production is as large as it was in the decades of 60s and 70s. So if you look at what is the relationship between agricultural yield and yield change and rainfall, on a smaller scale, these are the two lines which I would like to point out. This is rainfall during rainy season, and this is the grain yield. So if you are looking at, this is what would happen on a typical farmer's field. That is, if the rainfall is increasing, the gradient is much smaller. That is, if rainfall is much larger, you don't really kind of reap the benefits of higher rainfall, while this is on an agricultural station where economy is not a major problem. That is, they don't care how much money it takes to put in fertilizers or pesticides. And so obviously if the rainfall is higher, the yield is much, much larger in an agricultural research station as compared to in a typical farmer's field. And the reason is because the farmer tries to minimize his investment as he has no information about the seasonal predictions. He doesn't know what's going to happen in the season, or then that is in the months of June to September. So he tries to minimize his losses, and hence he tries to put in the minimum amount of fertilizers or pesticides, and that's why he doesn't really reap the benefit of a higher rainfall, because he has no information about it. So which is why I think seasonal prediction is pretty important. And what we are going to look at is how well CFS and other models, that is the seasonal prediction models, how well they capture the extremes of ISMR. So now we are going to look at seasonal forecasts with dynamical models. First we'll look at the mean climatological pattern, and then the inter-annual variability and its prediction. And we'll be using the retrospective forecast from ensembles. This was an experiment done about a few years ago. with all the seasonal prediction models of Europe, and with also with CFS separately, that is from the hindcast or the retrospective forecast of CFS. And ensembles cover the period of 1961 to 2005, while CFS has a shorter retrospective forecast going from 81 to 2009. So this is a seasonal mean pattern. When we talk of seasonal mean, it's basically from June to September, which is when it rains mostly over the Indian region. And what we find is that, okay, the mean pattern, this is the mean pattern for in observations. This is CMAP. This is from ECMWF. This is from GeoMar IFM. This is UK Met Office. This is Meteo France, and this is another center, CMCC. So by and large, the seasonal mean pattern is reasonable, though some of the models, such as Meteo France and UK Met Office, they have a tendency to underestimate the rainfall. That is, they have a bit of a dry bias, which is kind of common with most models. So if you look at seasonal prediction by ensembles models and also with CFS, and you look at how well the pattern is simulated, it looks reasonably well. That is, you are looking at a region 62. Yep.
Can I ask you, so your initial state, when you say seasonal prediction, gotten from hindcast reanalysis data?
Yeah, it is from, okay, the atmosphere will be coming.
Active data assimilation.
Yes, there is data assimilation, where they will be assimilating for the atmosphere, and they'll also be assimilating for the ocean. So it's, but it's not a combined data assimilation. They are doing it separately for both the components.
But is it done from a hindcast? Starting 2007 initial data with the knowledge of 2009 and everything else?
No. I mean, what they do is, let's say usually they start it, let's say, in a month. Like most of the forecasts that I'm talking about is what they kind of release, let's say, in the month of May, which is based on the April initial conditions. That is, you take the initial conditions, run it through a data assimilation package, both for ocean and atmosphere, and you get an initial condition based on it. You are now kind of, and of course, the background climatology is always there, which is the background state, which would be from the retrospective hindcast, let's say from 81 to 2005 or whatever. They would have taken a climatological period, which would be the background state, on which they will be adding the additional data that would be coming from all the sources.
Thank you.
Okay. And the pattern looks reasonable, but if you look at correlations of rainfall, there is all India rainfall with what the models predicted, that is single numbers for all these periods. Sorry. Oh. I don't know. It's always confusing. Huh? Yeah, it's much easier, or okay, I guess, yeah, this is much better. I'm used to it. So if you look at correlation between predicted and observed ISMR, this is what I would like you to look at. You see that it's kind of hovering around 0.4. And I'll talk about why we want to remove 83 and 97. And if you remove these 2 years, then you see that it kind of shoots up, but not very significantly. The number is about 0.4. So that's the number that we are looking at, and which means that it's not really great. You could do much better. What we would like, at least between the correlation coefficients, or between predicted and ISMR, to be as close as 1 as possible, and we are still far away from it. That's what it's saying. Yeah, CFS version 1 was only 0.14, and they changed a lot of things when they come to CFS V2. But okay, it moved from 0.14 to 0.41, and if you exclude those 2 years, it's 0.33 to 0.57. Rainfall to rainfall. Okay, you're taking the anomalies and then doing, in some sense, an anomaly correlation. Yes, it's an anomaly correlation. And if you look at rainfall differences in CFS V2, as we just discussed, there is a dry bias. That is, it rains much less over the Indian region. Both in, this is CFS V2, the later version, and this is CFS V1. And they underestimate the rainfall over the Indian subcontinent. And what I would like to point out is that they kind of overestimate rainfall over the equatorial Indian region, both in both versions of the model. And there is an underestimation of the rainfall over the El Nino region, or the Central Pacific and the Eastern Pacific. So are these related to SST differences? So if you look at the SST differences, both of them have a cold bias. That is, you have higher rainfall over the equatorial Indian region, but colder SST over the equatorial Indian region, and higher rainfall. So, and we know that quite a few models do that, and if you look at free runs of climate models, they have a similar bias, that is it rains too much over the equatorial Indian region and the SSTs are colder. So it kind of comes down finally, if you're looking at the seasonal mean pattern, to the SST, this is the SST biases, this is for models, they kind of tend to be, this is SSTs and this is its frequency distribution, and most of the models tend to be in the lower range, while the observations have highest SSTs, higher frequencies in the higher SST region. And this is the SST rainfall relationship. This is the observed pattern, and then you find that it kind of, most of the models overestimate. That is, for a given SST, you have more rainfall. So even if you have lower SSTs, you have higher rainfall. So that's kind of a compensation of errors that happens in models. Now coming to that was for the seasonal mean pattern. Now let's look at the observed variability of the Indian summer monsoon. And the blue are excesses and the reds are the droughts. And these are for the period from 1960 to 2010. These are the droughts that we got. And these are the years of excess rainfall. The last excess rainfall which we got was in 1994. That's almost 2 decades we haven't had rainfall exceeding 1 standard deviation. By excess we mean exceeding 1 standard deviation, and a drought means being below the normal by 1 standard deviation. So we haven't had a single excess year since almost 20 years since we had one. So if you look at how well the seasonal prediction models forecast these extremes, and we are going from excess to droughts. The leftmost one is 1961, which, at least if you're looking at the sign of the anomaly in the model, it seems to be catching it correctly. But if you come to a year like 1983, where this is the observed anomaly, this is what the models do. That is, regardless of which models you are looking at, these are all the ensemble models, the ones which took part in the ensemble, all of them fail to predict even the sign of the anomaly correctly. That is, you are looking at 5 models and each of them may be using about 25 to 50 ensembles. All of them, if you take the average of it, they seem to be saying that it would have been a drought, while in actual it was an excess rainfall. That is a major failure of in the hindcast. Similarly, 1997, which was one of the strongest El Ninos, when Indian monsoon was near normal, it was not excess, all the models again had a similar problem. But there are years when the droughts were reasonably well predicted, that is 1982 and 87. These were 2 major droughts and the model seems to be able to pick it. And this is the same thing for the NCEP models, and the 1961 is absent in it, but then again you can see that this is 1983, and again the model had a problem, and 1997 the models again had, these 2 versions of the NCEP models again had a problem. So if no matter what kind of model you're looking at, these are with different dynamics, different physics, they all seem to have a kind of a similar behavior when it comes to Indian monsoon. That is, some years they are just not able to predict it, and certain years they seem to be able to do reasonably well. So if you look at it as a hits and misses, this is what you get. You get a miss rate of about 0.4 or 0.3. This is for CFS1 and CFS-V2, and the correlations which we already talked of is about the order of 0.4. And hit rate is about 0.5, which means that only 50% of the time you are going to get it right. And we are not even looking at any fancy things. We are saying if the sign of the anomaly is right, we call it as a hit, and if it is wrong, we call it as a miss. So even with such a simple-minded yardstick, you're still getting only 50% of the time correct. And if you look at factors which have an impact on Indian monsoon, one of them is well known, which is the ENSO-monsoon link, and this is in observations. And generally, this is if the ENSO index as defined by us, if it is positive, then we find that rainfall is usually in this quadrant. There are of course outliers, and generally if it is negative, that is unfavorable, you are likely to have lower rainfall, and if you go in this region, there are no excess rainfall years. Certainly it could be near normal, like 97, which was an outlier, and so was 94, when there was a weak ENSO, but you got an excess rainfall. But on the other hand, if ENSO was, you had a La Nina-like conditions, a typical canonical type of that would be 1988. So ENSO could kind of explain some part of the variability. Was there any other factor that could affect the Indian monsoon? And that's the Indian Ocean, Indian monsoon link. And yesterday there was a discussion about what's happening in the atmosphere. That is, even if you may not have a dipole, it's quite likely that you may have a equino, which will have, if it's a positive equino as we define it, you'll have higher rainfall and higher convection over the western part of the Indian Ocean, and that seems to have a positive kind of a relationship with the strength of the Indian summer monsoon, while if it's clouding more over the Indonesian region, it's likely to have a more negative impact on the Indian monsoon. So we would prefer to use the term equino, because not all equino are related to the occurrence of a typhoon. And these are the details of the thing, and this is the year 1994 when there was one of the strongest positive dipoles. You had increased convection. This is SST anomalies here. This is positive and it's negative. That is, so related to that, you had higher rainfall, and this is what I'm showing is OLR, and you have higher rainfall and convection on the western side, and you got a fairly strong monsoon. Similarly, in the year 1997, when there was a strong El Nino, in spite of having a strong El Nino, we know that El Nino is usually unfavorable for Indian monsoon. We got a near year, again, in conjunction with a strong El Nino, there was a strong positive dipole or a positive equino, which kind of counterbalanced the effect of ENSO. So these are the details for 2 years. There was a positive dipole, which was August of 1994, when it was the strongest. You had positive anomaly and winds, which kind of went into the western region, the anomalous winds, and then this was 1986, which is the opposite of that, but then you had a negative equino, when you had higher convection over the Indonesian region and kind of less convection over the Indian region as well as the Western. So if we just take these two factors, can we explain extremes of ISMR? As Dr. Sikka told us, we are not interested in the mean, that is between plus and minus 1 standard deviation. What we are interested in is whether we can say the prediction could be, it is going to be beyond 1, plus 1, or it is going to be beyond minus 1. Those are the years which we are interested in. So if we just use these two factors, could we use ENSO and equino, a combination of that, and if you look at it on a phase plane, this is the dividing line, and you find that this is the equino, which is so if equino is favorable and so is ENSO, that's when you get very strong, that is 88, which is one of the strongest monsoon years. And if both of them are unfavorable, drought. So just using these two combinations, you could say that if both of them are unfavorable, it's unlikely that you'll have excess rainfall. And if both of them are favorable, you are unlikely to have a drought. At least that much we can say about the extremes of Indian monsoon rainfall. And this is another thing which is Francis and Solochna have kind of come up with a composite index of both of them, and this explains the same thing in a slightly different fashion, where you kind of take climatological probability of occurrence at 20%. And what I would like to point out is if the combined index is fairly negative, then you don't have any excesses, and if both of them are fairly positive, then you have higher, you don't have any droughts. So now let's look at how well the model simulate these two aspects, that is the ENSO-ISMR relationship and the equino-ISMR relationship. So this is the ENSO-monsoon relationship in models, and if you look at whether they themselves get the ENSO correctly, that looks reasonable between the correlation between the observed and predicted ENSO. For this is all for April initial condition forecast. It's about 0.82 in UK Met Office and kind of hovers to a low of about 0.65 in CFS V2. But if you look at the correlation with Indian summer monsoon, the observations kind of show a correlation of about 0.54, and most of the models, some of them have a lower correlation like ECMWF, but they seem to be in the right ballpark. You can't say that they are doing it too badly for the ENSO-monsoon relationship. But now if you look at the equino-monsoon relationship, I mean the first two columns are the same. I would like you to see the third column. I hope you can see it. Well, the observations show the correlation to be about 0.51, and most of the models don't even get the sign of the relationship correctly. That is, they're all negative, and fairly strongly negative when observation is 0.51. CFS V2, which is likely to be used in the monsoon mission, which is the major mission of the Indian government for predicting seasonal rainfall, it has a strong negative relationship with the equino. And if you look at the correlation of ISMR, that's the Indian summer monsoon rainfall with convection elsewhere, you find that it's positively correlated to the western box of the Indian Ocean, negatively correlated here, and over the Pacific region, it's a kind of a mixed signal. That is, if you are looking at extreme eastern Pacific, it's positively correlated. As you come towards the dateline, it's kind of getting negatively correlated to the region slightly west of the dateline. This is not exactly the same as what we think of usually. We think that ENSO is always unfavorable, but if you look at rainfall with convection elsewhere, that is rainfall elsewhere, there seems to be much more mixed signal than what you get from SST rainfall relationship, which is what most people look at. And this is what the models show. This is for ECMWF, which seems to get the equino relationship correctly. But I would like you to look at IFM, where the correlations are of the opposite sign. That is, it's positively correlated with the Indonesian region. That means if Indonesian region is raining higher in that particular model, it's going to be a excess rainfall here, which is kind of opposite of what you would get in observations. And similarly for UK Met Office, it's kind of a mixed signal. It doesn't get the equino signal at all. And a slightly more mixed signal in CMCC. And Meteo France also has a kind of an opposite signal, if you want to call it that. So it's certainly that the equino-monsoon relationship seems to be failing in most of the models. And this is the same thing for CFS. We have kept them separate because ensembles has a longer data set going from 61 to 2005, while CFS was only from 81 to 2008. So we kind of done them separately. But then again, the same signal seems to be coming out in CFS1 also. That is CFS. That is, it is wrongly correlated over the Indian region, and over the Pacific region, it's kind of over the eastern parts of Pacific, it seems to be negatively correlated, while in observations it seems to be a positive correlation for rainfall. So even as gross as something on a climatological pattern, sort of a seasonal mean pattern, the correlation seems to be going wrong in most of the models. So let's see what impact this has on predictions. This is the season of 1983 when we saw that almost all of them had a spectacular failure. And this is for CFS. On the right is on the left is SST anomalies that the model simulated. I'm now going to look only at CFS, except maybe once or twice for ECMWF, because the signals are very similar for all of them. And if you look at JJAS for 1983, it was in the dying phase of an El Nino. That is, if you look at the SSTs, they didn't show much of an El Nino, but all of the models simulated a El Nino. That is, in the middle of the season, it kind of switched from being an El Nino to a kind of near normal or a slightly La Nina kind of conditions. And that had an association with that. I don't know whether that impacted it, or associated with that was the Indian monsoon became stronger. But the models continued to predict an ENSO, and associated with that, they got fairly negative large rainfall anomalies. So that was maybe that was one of the reasons why they failed it. And the fact, this is for the season of 1994, when there was a weak ENSO over the Pacific. This is observation, while they predicted a La Nina. And even if they got the rainfall right, it was because for the wrong reasons. That is, they were predicting a La Nina, and they got a excess rainfall or near normal rainfall over the Indian region, though the prediction for ENSO, something as large as ENSO, was wrong for that particular year. So it's like you're getting the right answer for the wrong reason. And this is ECMWF, which was one of the few models which has both the correlations right, and it could, 1994, as we remember, had a strong positive equino. This is for observations, and the model could get the equino right, but it didn't have much of a La Nina, and it could get a reasonably good simulation of the Indian monsoon. So this is, supposing you just, we may be saying, okay, now the SSTs are wrong, which is why the models are going wrong. But supposing you feed in observed SSTs and just run AGCMs, this is what they do for 1994. This is an older MF. But what I would like to point out is almost all the models got it wrong. This is observations, and this is what the models predicted as Indian summer monsoon rainfall, or simulated, not predicted, sorry. Almost all the models got it wrong. This is an older MF. So if we look at the latest MF, I don't have data for all of them, but if you look at the AR5 MF, the story remains the same. That is, they are all still having negative anomalies This is for CCCMA for 1994, and this is for MRI for 1994. And both of them still seem to be saying that they're going to simulate a drought-like situation, even if you're forcing them with realistic SST. Looks like the problem still persists even in the present day, most of the present day models.
They also have the wrong correlation with the
Yes, this is with observed. Yeah, this is you're forcing with observed SSTs, but they're still getting it wrong.
getting the wrong thing.
Yes. So we did some experiments with our own AGCM, which is an older version of the NSEP forecast system. We were with the regular actual observed, like the one in AMIP, we got a drought-like situation. So we prescribed climatology over Pacific, and over India over the Indian region we prescribed SSTs as observed. And this was the control where you got a large drought for the year 1994. But when we prescribed it, the Pacific to be having climatological SSTs, it seemed to improve the simulation, which means that basically, as we saw, models are kind of much more sensitive to ENSO, and they somehow don't seem to be kind of sensitive to what's happening over the Indian region, that is the equino. And this is for 1985 when there was a negative equino, and models, and there was a La Nina-like condition, and models kind of simulated excess rainfall when it was a near drought condition. The rainfall was actually 9% below normal, very close to being a drought, but the models predicted that it would be a excess rainfall because they just kind of responded to it, and did not really respond to a negative equino. Now we come to season of 2012. This was an interesting season. This is from observations. This is the ISMR OLR correlations from observations, and this is the OLR anomaly for June to September for the season of 2012. So you can clearly see that OLR was positive here on the eastern side of Indian Ocean, and it was negative on the western side of Indian Ocean, which clearly showed that there was a positive dipole. And here it was kind of mixed. You had kind of slightly negative anomalies were part of Central Pacific and somewhat positive anomalies over the other parts. So it was, the total rainfall was about 8% below negative, but not a drought. It came close to being a drought, but then it kind of recovered, and this is what happened during the various seasons. The top one is for June, when the monsoon was really bad. We hardly had much of rainfall over in the month of June. So you can see large positive anomalies of OLR, but at that time, what I would like you to point out is that this equino was still positive. Similarly, in July, it kind of recovered and you had a positive equino, and though there was a lot of clouding over the equatorial region. And this is for August and September, and you can see that the equino signal persisted right through the season. So if we ask ourselves, what do the forecasts show? I'll show only for ECMWF. This is a correlation between convection and rainfall in the ECMWF model, and this is what the models predicted. They certainly didn't get an equino, and the rest I leave for you to see for yourself what the models are doing. And if you look at the ENSO forecast, this is the prediction from May conditions. This is what the observations did. In the middle of July, it turned from being increasing, strengthening ENSO to a weakening ENSO, the middle of July, and then kind of came to near normal conditions, while the model kind of forecast that it's going to be a strong El Nino. And that's what I guess the models were responding to. They respond very strongly to ENSO forecast, ENSO, and they kind of showed a drought-like condition. So this is what I... Okay, I mean, Dr. Sikka will say, because the monsoon strengthened, like the ENSO weakened. So I'll only talk of associations. I'll not talk of cause and effect. It's difficult to say that, but certainly there was an association that it became weaker, and yes, yeah, sure.
So I was just thinking of a naive reason why I'm not a doctor of these things, but when the ENSO weakens, Walker circulation, you get a stronger easterly jet, wouldn't you, over the monsoon region?
No, stronger west. If you are looking at the lower level, it's a stronger westerly jet.
No, I'm talking
upper level.
Upper level. Upper level easterly jet.
Usually upper level easterly jet is also related to the strength of the Indian monsoon rainfall, which is what I think JS maybe can answer it better, but because he has looked at easterly jet in a much deeper thing.
Okay.
And westerly jet also strengthens. That's as a kind of a response to the heat. Yeah, heating in over the Bay of Bengal.
That's the Walker circuit. That's what I was.
No, I don't think it's a Walker. No, there is no real Walker circulation of the Indian region. Yeah.
I just wanted to make
Which one? Oh, okay. Summary is okay. Rest is all a summary. So my final question is, I don't know the answer, and I leave it to you to say what is wrong. I don't know. I mean, there's something like all models, no matter what dynamics you're looking at, what physics you're looking at, what resolutions they are running, they don't seem to be getting the Indian monsoon linkage correctly. And I think that's the crux of the problem when it comes to predicting the monsoon on the seasonal scale. There could be other problems on shorter scales, but certainly for that. And finally, I would like to acknowledge.
Yeah, I wanted to make a comment on 2012. This 2012 El Nino, so to speak, was very peculiar. We never saw much signal in the atmosphere at all. If you go back to your slide for June 2012 and July 2012, you see there is not much of a flaring up of the convection over Central Pacific at all. So this year the El Nino itself was very, very peculiar. You saw signal in the SSTs all right, 3.4, but for some reason there was no signal here. But I would like to point out another peculiarity of this season, which I had never encountered before, is look how much West Pacific has flared up. The number of typhoons that occurred in the West Pacific in June and July must have broken all records, I think. And for some reasons that we don't understand, I think that led to a suppression in the Bay. So despite the Equino being favorable, it would have been much worse had Equino been negative. Then we would have surely made it to a drought. But because Equino was favorable throughout when this negative factor went off, so this is a third factor now we have to worry about. But again, it is only a conjecture.
I just wish to say that there is no parameter except ENSO which is related to 0.5 or 0.6 with the Indian routes as a single parameter. Equino or anything, no parameter is there. So it is the most dominant signal. So you have to go by it and then watch it, how the Equino is turning. Or if, because you are unable to forecast an Equino, if you are able to forecast, with regard to ENSO, the forecasts are fairly reliable 3 to 4 months in advance. They are able to say that the signal will, in this year also, the Equino signal in the SST was clearly demonstrated 2 to 3 months earlier in the month of May itself. It was there, it is going to rise. How much it will rise, when it will collapse, that is a different details, So, we may try to kill that ENSO is the boundary conditions are not that important. I think the boundary conditions of ENSO are most dominant, isn't it?
It is dominant.
Other thing is that
that's
in
not
the
the only
case,
thing that controls
another peculiarity
ASMR.
which is there is that in the case of season has got daily rainfall, all India daily rainfall, and it has got also departure of the daily rainfall by 10%. There is not a single year, you can check with your data, isn't it, in which if there is a El Nino going on and the spell of wet has exceeded more than 1 day in the season. That means the extreme wet, somehow the boundary conditions of ENSO are so crucial that the season as a whole remains, the rainfall, daily rainfall doesn't become excessively positive. So that is also a very important feature which is there, and that is not there so much with the Equino. So there is a thing, that is why the independence of Equino, yes, there are some independent episodes, but many of them are also linked along with the ENSO.
The Equino is probably a basin scale divergent wind largely, because it seems to blow from the near equatorial, I mean, roughly speaking, heat source, heat sink related, or high pressure directly towards low pressure. To ask a model which is already having difficulties in predicting the Hadley and Walker circulations, those big divergent circulations, and to have a basin scale divergent wind, I think we're asking a lot more work has to be done.
Can I respond to that? You're absolutely right. The wind index is a problem, but we have just now, the actual key to Equino is the OLR anomaly. And OLR is, so we have actually now switched over to an OLR index, which is robust, but I agree with you if you have problems with ITCZ simulation over other regions. This is a matter of simulation of convection between east and west, and you're likely to have problems. But the fact that we used to use a wind index, now you can forget. We have gone over to a much more robust index, which is OLR.
Any more questions? If you don't have any questions, can you answer the last one? The base state is wrong on the model. Okay.
Possibly.
So let's thank